Hi viewers, you're welcome to another episode of Staad Pro. In this episode, I'll be showing you how you can model and analyze a cantilever retaining wall. So let's get into it. You go to new projects and then we just create space. Then you can give it a name. Let's give it retaining wall. Okay, then you can pick meter and kilonewton. So click on next and then add beam. So finish. Let me show you the picture of the retaining wall that we want to analyze. Alright, here is the picture. You can see we have the wall, the stem of the wall, that is 2200 mm, and we have the base. The base is about 2000 mm, because you can see the back here you have 500 mm, and then between here and here, that is 300 mm, that adds up to 800 mm, and then you can see the toe here, you have 1200, and that adds up to 2000. Okay, so you can see the base is 2000 mm, the stem is 2200 mm, and we have a heel beam here that is dropping by 450 mm. Okay, so the unit weight of the soil is 18 kilonewton per square meter, and then the backfill is filling up to the top surface of the wall. You can see where I have the backfill. Okay, and then here you have the natural ground level, so you can see this depicting the soil. All right, so this is what we are going to model. So we can see that the thickness of the wall is 300 mm. Also the thickness of the base is 300 mm. Also the thickness of the heel beam is also 300 mm. All right, as far as you know in Staad Pro, before you can model any element, what you should be concerned about is the points you'll be needing the nodes. Okay, so we need to know where we'll be having the nodes. So let me just depict the points that we need the nodes that will enable us to draw the model. Okay, so let me pick this. So at this point we'll be having a node. Okay, so this is the node that will depict the beginning of the wall. All right, and then here we'll be expecting another node which will depict the beginning, which will depict the end of the wall. Okay, so here we'll be having another node that will be depicting the beginning of the wall, and also here we'll be having another node which will be depicting the end of this wall. Remember that the wall doesn't end here. The wall should come to the center of this base to see so that you can get the proper connection. Okay, so the wall is basically from this top up to the center of this base. Okay, and then we'll be having another node here which is the end of the heel beam. Also we'll be having another node here which will depict the beginning of the heel beam. Okay, so these are the points where we need the nodes. You may be wondering why I'm having the nodes at the center of the element and not at the top or at the bottom. Okay, this is how Staad Pro works. Staad Pro works with center to center, not top or bottom. For example, if you have an element like this, and the thickness of the element is 300 mm, in Staad Pro you are supposed to draw a line like this. Okay, so when you want to give the thickness of this element as 300 mm, Staad Pro will take 150 to this side, 150 mm, and also 150 mm to this side to complete the 300 mm that you are assigning to that element. Okay, so whenever you want to model any element in Staad Pro, make sure you are putting the node at the center of that element and not at the top of that element. So let's go back to Staad Pro and start inserting the node. So I will start with this one, which will be at 0 0 0. I mean, 0 on the x, 0 on the y, 0 on the z. So you go to Staad Pro. Let me close this, and then I'll start by inserting the node. So I'll put one here, 0. All right, then I'll put another one at the last edge here. Okay, so that should be 2 meter. Remember, from here to here is from here to this point is 500. From here to here, that's 300. I'm talking about this 500 plus this 300, and that adds up to 800. Then plus 1 2, that is 2000. So it means this point will be 2000 on the x. Okay, so that is 2 meter. Remember 2000 mm, but here it is meter, so that should be 2 meter. Okay, so we have the node here and we have another here. Let me put this in front view so we can see that. So the next one is this node. This node is at the center of this wall, definitely. Okay, so from this point up to this point, that is 500. So I'm just going to add 500 plus half of 300, so that should be 500 plus 150, and that gives me 650, which is 0.65 meter. Okay, so I will add one more here, which will be 0.65 on the x. All right, so I have this as well. So I have this node, I have this node, and I have this node. So let me deal with this other node. Okay, so this node should be this particular node should be 2000 mm minus 150 mm. Remember that the width of this toe beam is also 300. If I subtract the half of this width, which is 150, if I subtract it from the whole length, which is 2000, that will be 2000 minus 150, and that will give me 1850. Okay, so I will have this node like that. So let me go here and have 1850, which will be 1.85. Okay, so I have the node here. Okay, then remember that this point is 0 on the y. I mean the center line across this base is 0. So now I'm coming to this level, so that should be minus. Okay, so the distance from here to here, that should be 450 plus the half of this base, which is 150. So that should be minus 600. 450 plus 150, because I'm coming downward, that should be that should be minus. So I will have 1.85 in the x, okay, because it's the same level with that, and in the y I will have minus 0.6. okay, then you can see the node at the bottom here. All right, so that is looking good. Then I can have this one. All right, I can have this one. Remember that the position of this node is 500 plus 150. Okay, so it means on the x it is 600 mm. Okay, then what about on the y? The height from this point up to this point, that is 2200. Then we are going to add it to the half of this base, because the wall shouldn't be coming at this point, it should be coming from the center of the base. So that will be 2200 plus 150, and that will be giving me 2350. Okay, so it means that in the x that's 600. Sorry, in the x that is 650. Yeah, 150 plus 500, that's 650. So in the x that is 650, and in the y we have 2350. Okay, so in the x I can have 650, which is 0.65, and in the y I can have 2.35. okay, so here we are. So I can start joining them with beam. So let me pick beam. Actually, we don't need beams in retaining wall, but I'm just drawing the beam so that I can use that to get my modeling. I will later delete them after. Okay, so I will draw the beam from here to here. Then I can have this to here. That represents my base. They can have one from here up to this point. And then for the heel beam, I can have this and this. Right? So let's see in 3D view. So this is making more sense. Okay, and then the retaining wall, the length of the retaining wall is 30 meter. I mean the length. You are seeing this section here. You still have to see the length, the long length that is going inward. Okay, so that is 30 meter. All right, that is 30 meter. So that means I will have to copy all of this again. I will copy it in the z direction to go inward, so I can have it by 30 meter inward. So all you just need to do is select all of the beam. Remember, when you select the beam, the node will follow, so I don't need to select the node. Okay, and if you want to select the node, you can just use the geometry cursor. Geometry cursor can select the beam and the node together, but it doesn't matter. I can also use the beam cursor, because when I use the beam cursor, I know the node will follow, but don't use the node cursor. So I go to translational repeats, then I'm repeating in the z direction. So how many numbers? I just need one number, and the default spacing, that is 30 meter, but that should be minus 30 because we are going inward. And then you click on OK. All right, so we have it over here as well. So that is very simple. let me maximize this. All right, so now all I just need to do is to join the nodes with plates. Then I pick the 4 noded plates, which is this. Then I connect this one and this and this. Okay, so I have that plate. Also I connect this and this and then this. Okay, so I have that also. Now I will use this one, which is the generate mesh. So I will generate mesh from this point to the last point here. Okay, and then this last point, this point, and then back to the point, this point here. Okay, so I'll be using a quadrilateral machine. Okay, then how do I want to distribute it? Here I can have let me use 15, and here I can just use, that's 1.35 meter. Let me use 3, and let me use 15. Then you click on apply. Then I have that mesh. Okay, then I have to create for the other side, that is this point, this point, and then the last point. So quadrilateral. Okay, I think, okay, it is different. It's 0.61. I can just have one mesh, and here I can have 15, I can have 1, I can have 15. Then click on apply. Then I have all of the mesh like this. You can see that we've created plates, but we used 2 methods. Some we use the 4 noded plates, and some we use the generate mesh surfacing. Okay, all right. So now I just need to delete all of the beams. I don't need any beam. I just use the beam in generating. Okay, yeah, this beam. So you just select it like that, and then you delete them. Okay, so that is good. Then we move to the next step, which is the thickness. We need to apply the thickness. So you go to general, then you go to property, then you can go to thickness. Okay, not define anymore. So you go to thickness. Thickness is for plates, while define is for elements. I mean the beam and the column. So you go to thickness, and the thickness of each one. Let's see. The thickness of this wall is 300 mm. What about this base? That is 300 mm, and then the EU, that is also 300 mm. So that means we have the same thickness for everything, which is just 0.3. So I only add this, and then click on add. So I can close now. I can even assign to view, since everything is 0.3. So assign to view, and then you click on assign. Okay, so everything has been assigned. Let's see in 3D rendered view. Close this, and then you can maximize this. Let me pick this. Okay, so this is how the retaining wall looks like. Okay, so you can see that this portion that we did the meshing, you can see the meshing, and here that we didn't do any meshing, you can see that there is no meshing. So I close that. So we go to the next step, and that should be assigning the support. So you go to support, and then I only need one support, which is the fixed support. Click on create, and then fixed support. That's the first one. Click on add. Then let me put this in front view, and then I need to click on this support. Here I'm expecting support. Also here where I have the wall, I'm expecting the support. Here where the base is touching the ground, I'm expecting the support, and here where it's cantilevering a bit, I need the support. All right, so click on add to selected node and click on assign. Then yes, then we have that. You can put it back in isometric view. Then we have the support for all of those. Okay, then the next step will be assigning the load. Okay, but before I do that, I want us to talk about the loadings. Okay, all right, remember that this is the point where you have the backfill. Okay, so you have the backfill at this point. So this is where the natural ground floor is. So whatsoever soil you are using as backfill, we'll be having a uniformly varying load. There will be maximum at the bottom, and there will be minimum at the points, almost near zero at the points. Okay, And also at the bottom here where you have the heel beam, you'll be having the same thing. You'll be having a triangular load, but this will be passive. Okay, so you'll be having the same thing, but on this wall, you know, the backfill will also be exacting a vertical load here, but here you'll be having a uniformly distributed load, so that is good. Here you don't have a backfill, so we are not expecting any load here. Okay, so the load we are expecting is the load on this wall that will be acting horizontally on this wall. We'll be expecting another horizontal at the heel beam here. I'll be expecting a vertical load that will be on the base. Okay, so you go to load, so and then you go to load cases. You can click on add. Then I will just create one load case. I can even call it load case 1. I don't need to change it. Then I will call that let me call dead. All right, let me give it a name. Let me call it dead load. Then you click on add. I can have another one. Let me call it maybe still dead load, but let me just call it load 2 or dead load 2. So that's still dead load. Then you click on add. Then I can have another one. Let me call that live load. Okay, then I can change this to live. All right, then click on add, and then I can create a combination. Let me take all of this here. Then this load case 1, that's a dead load. I'll be using 1.4 for the factor. Load case 2, I'll be using 1.4 as well for the factor, and this I'll be using 1.6 for the factor. I can change the name. Let me change the name to ULS. I can just give it a name, and then I click on add, then close. Now let's start assigning. This one that I called dead load 1, I will only add one load there, and that will be the self weight. So click on add, and then the self weight, make sure the self weight is there. Okay, you can see the self weight. Then you just click on add, and I can close that. Let me minimize that. So I go to load case 2. Under the load case 2, that is where I will add more of the loads. So go to add. Now the first load I will be adding, that will be this triangular load. Okay, that will be this triangular load. All right, and then the triangular load will basically be the a pressure, you know, a trapezoidal pressure, and that is just the backfill, which is this 18 kilonewton per squared meter, which is the unit weight of the sand that we are using as the backfill. So go there, and then let me pick this plate. All right, then you go to symbol and label, and then you go to plate orientation. You can click on OK. Then let's see the plate orientation. You can see the plate orientation. Look at this direction. This is telling you that this is your local Z. This is global. You know, this is global axis. All right, you know, the global axis, this is X direction, but when you check this, this is local axis. So you can see the direction of the local axis. The local axis tells me that if I am moving like this, that is my positive Z. Okay, but this is not the point that I want to add my load. I want to add the load at the other end. Okay, so that means I will be working with the negative Z direction, in as much I'm working with the local axis, not the global axis. Okay, so when we get there, you understand that more. And then I can go back to the symbol and label. You can select it again so that you can take that away. Then you can click on OK, so that will move away. All right, then I can go back to the load case 2, click on add, and then you go to plate load, and then you can come to the trapezoidal load. All right, okay, so for the trapezoidal load, you know, we are working, you can check this diagram, that will help you. You know, we are working with the wall. We are working with this wall, remember. So at this point, we are expecting a load of 0, because you can see that the load is high at this point, and then it is now reducing up to the top. So at this top, you are expecting a load of 0 kilonewton per square meter, and then at this bottom, we are expecting the maximum, which will be 18 kilonewton per square meter. All right, so it means at point 1 I should be having a load of 0, and at point 2 I should be having a load of 18 kilonewton per square meter. So let's go back to Staad Pro. So you can see the unit is kilonewton per square meter already. So it means at point 1 I'm expecting 0, and point 2 I should be expecting minus 18. Make sure this is in local Z. I've checked the local Z. The local Z is what you'll be using. You are not using global, so you'll be using the local Z. But remember that we need to use negative, as we've seen the other time, because the positive side is not what we are applying the load, but the negative side. So the negative sign needs to be there. Now it is asking you another question. How do you want to vary the load? Should the variation be along the y direction or along the x direction? It's talking about the global now. So let's see. Of course, this is a wall, all right? So we are varying along the y, we are varying along the y, which is the global y. So you can pick vary along y, then you click on add, then we can close that. All right, so what else we will be adding? Okay, we are still expecting a load here, also a triangular load. We are still expecting a load here, also a triangular load. So I can add that. It's still a plate load. Under load 2, I can click on add, and then you still go to plate load, and then you can use trapezoidal. Under point 1, that is 0, and under point 2, that will now be 18, not minus 18. Always check the diagram. You can see this is 18 now. This is the direction at which I'm applying the load. It is different from this one that is going like this. This one is going like this, whereas this one is going like this. So this is the positive z direction. Okay, so this should be 18. But in case that is different, you can always change it. And then this is local Z. We are still varying along the y direction. So click on add. Then you can close. We also need to add load on this plate. Remember that the backfill you are having here will be applying a vertical load on this base, on this portion of the base. Okay. So and that load is basically the 18 kilonewton per square meter multiplied by the height of the backfill. The backfill is filled up to the top of the stem here, so it simply means 18 kilonewton multiplied by the height, which is 2.2. okay, which is 2.2. So you can say 18 multiplied by 2.2. So let's check that. You can go to tools, and then you go to calculator, and then we have 18 kilonewton per square meter multiplied by 2.2 meter. I can put this in normal. Okay, so and that is what 39.6 kilonewton per meter. 39.6 kilonewton per meter. That is going to be the uniformly distributed load. Okay, so click on cancel, and then you can still go to load 2, click on add. You will not be using the member load. The member load is for beam. Member, when you say member is beam and column. So you always come to the plate load. Here I'm having a pressure on full plates. This should be pressure on full plates. This is not a concentrated, of course, and this is not partial. It is not hydrostatic because it's not water. So we'll be having a concentrated plate. No, sorry, a pressure on full plate, and that should be what? Minus 39.6. Okay, that should be global. But right now I don't want to use the local, let me just use the global. I'll be using the global y. Okay, so I'll take it from the local z. I'll be using the global y. So that is y direction, the global y direction. So that should be minus 36 because the load will be coming downward. So click on add, and then you can close. All right, that should be all. However, we will still be having live load. A live load that will result due to rainfall. When rain falls, you will be having more load because the soil. Let me show you the picture. We have a backfill here, which is a soil, which can be a cohesive or a cohesionless soil. All right. But when rain falls, definitely the soil is going to absorb water, and then the weight of the soil will increase. Thereby, there will be more load on this stem, which is the wall, and there will be more load at this portion of the base. So that is the concept of the live load. So the live load is the load that we are expecting. That is the load of the water. I will be assuming the maximum point, that is the load is filled up to the maximum here. The water is filled up to the brim here. All right. So that means that I'll be using, still a triangular load for the wall, and then that will be a uniform load on the base. But what will now be the value? Then the question will be, what is the unit weight of water? The unit weight of water, that is 9.81, right? 9.81 kilonewton per meter squared. So it means you'll be having a triangular load here, and the value will be 9.81 kilonewton per meter squared. And here we'll be having a UDL, which will be 9.81 multiplied by the height, and we said we want the water to be to the brim, which will be the maximum, so that will be 9.81 multiplied by 2.2, so that will be the load that will be on this portion. Okay, so let's go back to Staad Pro and add that. So I'll go to live load, and then I can click on add. So I go to plate load. I'll be using the trapezoidal load first. So for 0.0, it will be just as we did for the soil. So this is 0, and this will be minus 9.81, and then we are varying along the y. This should be in local z, so click on add. Then for the second one, that should be pressure on full plates, and then what will be the value? Let's use the calculator. Go to tools, and then you go to calculator. Then that is 9.81, that is the unit weight of water, multiplied by the height, that is 2.2. Go to normal. That will give me 21.58. Let me assume 22. So that is 22 kilonewton per meter. Okay, so let's go to live again. Then we add. Then we can go to plate load, and then pressure on full plates. I'll be adding minus 22 because it's coming downward, and I'll be using the global y. Okay, but you can also use the local, but make sure you check the direction of the local axis as I showed you earlier. Okay, but since I have the global, I'll just prefer to use the global, and then click on add. So, and then you can close that. So now let's start by assigning the loads. I have the dead load, and under that I have the self weight. Every element we have the self weight, so I can just assign to view. Click on assign. Yes, so every element has the self weight. That's good. Then the next one is this one, which is the trapezoidal load. The trapezoidal load will be applied to this this plate. So you need to click on that plate, and you can say assign to selected plate. Click on assign, and then yes. Okay, so let me try to zoom so that we can see how that is. Okay, you can see, right? So you can see it is maximum at this point, and at the top here you are having 0. So let me close this window, and then that is looking good. Then we can move to the next one, which is trapezoidal. The trapezoidal load that will be applied to the bottom here. Let me pan inward a bit. Then you can use this. Then let's try to see this side. Okay, so just pick your plate cursor, then select this plate. Okay, then you can now assign to selected plates. Okay, and you can see how the direction is. All right, you can see how the direction is, so that is looking good. Let me close this window. That's good. Then the next one is the uniform load. I can put this in front view. Then I select this plate. Then use plate cursor. Then you select this plate, right? Then you click on assign to selected plates. Assign. Yes. Then you can see the use pan. Then you can see the UDL. So let me try to scale it in case of maybe I'm just. So go to scale and apply immediately. Okay, so apply immediately, and then you can see this is pressure. So you scale that. You can see the pressure. You can see now it is being scaled. So I think this is enough. Then you can close that. So that is scaled enough. Then we can go to the live load. Let's assign the live load for the trapezoid. No. Okay, this second one should be applied to that selected. So let me just click on it. Assign to selected. So we have that here, and then the next one, let me use the plate cursor. Let me put it in my view. Then select this plate. Okay, no, this select your load first. You have to select your load first, and then you select the plate. So click on assign to plates, and then assign. Okay, and then the load has been assigned. So now we have all of them. Let me close this. We just need to analyze. So to do that, go to analysis and prints, and then you click on add, then you can close. Alright, so after that, go to analyze, then you run analysis, save. Alright, good. You can see we have 0 error, 3 warning, 0 notes. So you can check the warning. So I'll go to post processing, click on done, and then you can click on OK. So what I will just check here is the plate stress. So you can go to plate stress, then so let's check the maximum vomits, and then you click on OK. Then you can see, all right, so you can see where you have the red, you can see the purple, you can see the green, you can see the blue, and you know what that looks like. Okay, so you can see 7.17, that's the red. So you're having that around the heel beam here. Okay, so this is everything you need to know about the analysis of the cantilever retaining wall. In the next video, I'll be showing you how we can design this using RC Designer in Staad Pro. Make sure you leave a like behind for this video if you like the video, and if you haven't subscribed to my YouTube channel, ensure you subscribe to my YouTube channel because that is very important to me. Thanks for watching.